Hello guys, welcome back to another video on my channel. Let us continue the linear algebra lecture series that we have started. Okay, so far, and I'm hoping everyone has watched the videos before this one, so that nothing is really new to you. So far, we defined linear subspaces of vector spaces. That was the last video, and studied how to sum them via the direct sum operation, so that we preserve the algebraic structure that comes along with being a subspace of a vector space. And we will talk about what generates a linear subspace, which is also known as a list of vectors. Now, the definition of a list is such that a list can only have finite number of elements. If there were infinite countable infinite number of elements, it would be a sequence. So we will only be working with lists for this series. And again, note that, again, as I said, we will be working in finite dimensions, whatever that means, which is just the list size. So the list size would be finite, which, is kind of true by the definition of lists, that lists have finite elements in them. And that will be the theme of this series, to work in infinite dimensions. That is, well, a completely different and advanced topic of linear algebra. So that's really out of the focus for this series. A sum of scalar multiples of the vectors in a list is called a linear combination. So let's define this more mathematically, more rigorously. A linear combination of a list v1 through vm, so it has m elements, m is finite, of vectors in a vector space V, is a vector of the form a1 v1 plus so on am vm, where the a1 am all belong to the field. So this v1 through vm are vectors in our vector space, and a linear combination or a vector of this form a1 v1 plus dot dot or am vm must also be a vector of V, because of the postulates, the linear algebra structure and properties that we had, that uh, these scaled sums of vectors must also be in the vector space. So indeed, that, this, it's true that this combination, this linear combination here, is a vector. An example of this is, let's take R3, the three-dimensional Euclidean space. So we have the vector 2, 1, minus 3, and 1, negative 2, 4. Again, since this is R3, every element, every vector of R3 is just in the form of this kind of tuple with 3 entries. So these are the two vectors in our list. We have a list of two vectors, this vector and this vector. Then we see that 17 comma minus 4 comma 2 is indeed a linear combination of the two vectors in our list, because we can take 6 times the first vector, add that with 5 times the second vector. So in our case, in this general definition case, we have v1 and v2 as these two vectors. If we set a1, the first scalar, to be 6 and the second scalar a2 to be 5, we get this vector that we had on the left hand side. So this vector 17, negative 4, 2 is a linear combination of the two vectors in the list. But, and you can again try all kinds of values of the scalar field. 17, negative 4, 5 is not a linear combination. No matter what scalar values of a1, a2 you try, you will never have an equation of this kind for 17, negative 4, 5. So that is a non-example, and this one is an example. Now, moving on to uh, a useful notion of linear combinations, where linear combinations will actually come up, is span as a noun. So that means is the set of all linear combinations of a list of vectors v1 through vm in vector space V is called the span of vectors v1 through vm, denoted by span v1 comma through vm. More precisely, and this is the set definition of a span of vectors v1 through vm is all linear combinations. So a1 v1 plus dot 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 plus am vm, where a1 through am range over all values of the field. So take these m vectors and just add them, take linear combinations of them over all possible values of the scalar a1 through am. That space, and again, we will prove that this forms a subspace, that a span is actually a linear subspace in V. This subspace is called the span of all possible linear combinations of vectors in a list. And we're defining the span of the empty list. Say you don't take any vectors, that's the empty list. We define that to be just the trivial element, which is 0. Every vector space, every linear subspace has 0. So the empty list of vectors should should span just the 0. An example before we proceed. So using the example from before where we had these two vectors 2 1 negative 3 and 1 negative 2 4, we wrote 17 negative 4 2 as a linear combination of the two vectors in the list. So that means from this new notation, new terminology, that 17 negative 4 2 is in or belongs to the span of the two vectors. And similarly, we had a non-example 17 negative 4 5. We can't find any scalar such that 17 negative 4 5 is a linear combination of the two vectors. Thus, 17 negative 4 5 does not belong in the span of the two vectors. That's just um, using the linear combination terminology from before and making it a little more geometrical, in the sense of now we have a linear subspace which consists of all of these linear combinations of vectors in a list. And if a vector is a linear combination of the vectors in the list, then it belongs to that linear subspace, else it does not. So now we have a notion of things lying geometrically in a space if they can be expressed as a linear combination. Here's an important proposition, and here's where we will prove that the span is a linear subspace. So proposition, the span of a list of vectors in V is the smallest subspace of V containing all vectors in the list. So there's two things we need to actually show here, that the span of a list of vectors in V is a subspace, and then when it is a subspace, it is the smallest subspace that contains all vectors in that list. So let's first show that it is a subspace of V. And to do that, we have those three criteria from the last video, that the 0 element should belong to the linear subspace. It should be closed under vector addition and scalar multiplication. So suppose v1 through vm is a list of vectors in V. The 0 vector is in the span of v1 through vm, since you can write the 0 vector by taking the zero scalar. Remember, we had an a1 v1 through am vm. Set all the a1 through am to be equal to 0, because again 0 is an element of the field. So once we do that, we have 0 times each vector, which was just defined to be the zero vector, and all of them will add up to give zero. So you can write zero by setting all the linear combination coefficients to zero. So therefore, zero does actually lie in the span because you can write it in terms of this kind of linear combination. Okay, that's first criteria done. Now let's check for the closure under vector addition. We have for A1, B1, dot 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 AM, BM, such that all of them belong to the field F. So we're taking two distinct elements in the span. So A1, V1 plus dot 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 AM, VM is one element, plus B1, V1 plus dot 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 BM, VM is another element in the span. When you add them up, you can use the associativity property to club all these coefficients of V1. So you have A1 plus B1 bracket V1 plus dot dot dot, do all of the same for the rest of them. So we have AM plus BM VM for the last one. And since A1 plus B1 is in the field for A1, B1 in the field, and similarly for rest of the elements, rest of the coefficients, because the field is closed under addition of elements in the field, it is indeed in the span again. So vector addition is in the span. What about scalar multiplication? Let's take lambda along with A1 through AM that's in the field. So if you multiply by lambda to an element of the span, so A1 V1 plus dot 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 AM VM, you can distribute lambda over each term in the sum. So lambda A1 V1 plus dot 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 lambda AM VM. Lambda times A1 is another element of the field. A field is closed under the field multiplication. So lambda A1 is some other field number. Lambda AM likewise is some other field scalar. And that means this is again in the span of V1 through Vm. So to prove that the span was a linear subspace, all we needed was existence of the zero element, the additive identity in the field, the closure under field addition and field multiplication. That's all we needed to, this was just following because of the way we've defined fields or action of fields on this on our vector space. So we've shown that the span is a linear subspace of V. Now to show that it is the smallest subspace of V that contains each vector in the list. So let's take Vk, a random vector in the list. That Vk is a linear combination of the list V1 through Vm. How do we see that this is indeed a linear combination? Set the coefficient of Vk to 1, which is ak. Set ak to 1 and all the other coefficients, all the other a's to 0. So in that way, you can see that, you can write Vk as a linear combination of the vectors in the list. You can do this for all k going from 1 to m. So all vectors in the list. So that means that Vk belongs to the span of the m vectors for all k equals 1 through m. Because you can do this, you can show that each element of the list can be written as a linear combination of the elements of the list. So therefore, it must be in the span, by definition of the span. Now suppose B were the smallest subspace containing all the Vk for k equals 1 through m. Then since it is a linear subspace, B must contain all the linear combinations of things it contains. We in this, the first assumption, what we supposed the B contains all the elements in the list, and since it is a linear subspace, it must also contain all the linear combinations of elements of the list, because it contains the elements of the list. This is by definition of, or one of the properties of being a linear subspace. So that means it contains all the linear combinations of v1 through vm. That means, which is just the span. All the linear combinations is just the span. So span of the m vectors must be inside B. So uh, improper subset B. But B was, when we suppose, the smallest subspace that contained Vk for k equals 1 through m. So that contained all the vectors in the list. Therefore, the span, which was also a subspace that contained the list vectors, must be larger than it, or B must be inside the span because B was the smallest subspace. So B must be inside span, so B improper subset span. And from before we have span improper subset B. So using both of them have to be true. We must have that span of V1 through Vm must equal B. And that's it. So the span is the smallest subspace of B that contains all the list vectors. That's it. That's what we had to prove. We're done. Now the other important bit of the span as a verb. So if span of the m vectors v1 through vm in a list equals v, this makes sense as subspaces. So if this subspace is equal to that subspace, or in this case, which is the entire vector space, then we say that the list v1 through vm spans v, capital V. Okay, nice. Let's talk about examples to make this a little easier. So suppose n is a positive integer, then we can show that this list of n vectors, where you have 1 in the first position, 1 in the second position, so on, until you have 1 in the nth position, spans Fn, where F is the field, of course. Take an arbitrary element of Fn, it will be a tuple of n field scalars. Let's call them x1, x2, dot 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 xn. Then you can decompose rather this x1, x2, xn as x1 times the first vector in the list we had, plus x2 times the second vector, plus dot 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 xn times the last vector. And you can verify that this indeed is equal to the left hand side. So what that means is we've expressed any arbitrary vector of Fn as a linear combination of the n vectors in our list, which means x1 dot dot xn belongs to the span of the n vectors. And that's it. That's enough to prove that the span of these n vectors is the entire space Fn itself. So there you go. The span of these n vectors, or rather these n vectors, span the entire vector space Fn. And we're using span as a verb here. Now an important point is a vector space is called finite dimensional if some list of vectors, and again when we say list, we mean finite length, lists are finite length, in it spans the space. So there must exist some list that spans the space. Then a vector space is finite dimensional. If you can't find a list of vectors, then the vector space is of course infinite dimensional. So what does it mean for a vector space? Rather, what's a more tangible example of an infinite dimensional vector space? It sounds quite romantic, but or sensationalized, but the simplest example is if you take V to be P of F, the set of all polynomials over the field F. So that means any general vector or element of P of F looks like small p of z equals a naught plus a1z plus a2z squared plus dot dot dot. So there's no end to how many powers of z you can have. You can in theory you can have infinite powers. And note that these coefficients a0, a1, a2, dot dot dot, they all belong to the field. And since it's a polynomial over field f, when the plug-in values that the z will take will also be from the field. So p of z is a map from f to f, from the field to itself. Take any list of vectors in pf now. And when I mean list, of course, I mean it has finite number of elements. Let m denote the highest degree of polynomials in the list. A degree is the highest power of z for a given polynomial. So take the highest degree of the polynomials in the list. So you can have x squared, z squared polynomial, a z cubed polynomial, z to the fourth. We want the highest in that list, the maximum degree of that list. And a maximum makes sense because it's a list of finite elements. But clearly, the polynomial, we can call the highest degree of all polynomials m. Then the polynomial z to the m plus 1, the polynomial with degree plus 1, 1 degree higher than the highest degree of your list, that polynomial is not in the span of this list because all the polynomials you can do a linear combination of all those polynomials, and they will be also again of degree m, at most m. You can't write the z to the m plus 1 as a linear combination of polynomials of lower degree. So this polynomial with one higher degree is not in the span of this list. And since m was arbitrary, you can show that no matter how large your list, there will always be a polynomial with a degree that's one more than the highest degree of polynomials in your list, which is not in the linear span. So you can't span your entire space with these lists of finite elements because the degrees of polynomials of any general element of or vector indeed extends to infinity. So no list spans P of f, and P of f is therefore an infinite dimensional vector space. That's the big example. I hope you like this example. It's very simple out of the more convoluted ones. In infinite dimensions, again, I'll mention as an aside, the definition of a linear combination does not really change much. You still have lists. You consider finite sums, but you have the distinction of a closed linear span, a linear span and a closed linear span. And I'm gonna leave it at that. I hope you enjoyed this video. Please like and subscribe to my channel, and peace out.